Okay, in the last class we discussed about the charge conjugation and parity symmetry, and then we showed that the CP symmetry violates, particularly in case of kaons. We discussed about the scenario in kaons where we have a different eigenvalue for the CP symmetry. So we will start from there and we will continue that up to here. Okay. So in the last class we discussed about the CP symmetry. Okay. So in CP symmetry, that we will first consider the charge conjugation, then followed by this parity operation. So both those operations we have to perform in that particular reaction or decay or interaction, and then we check whether that reaction is possible. And if it is possible, then that particular reaction is conserved under charge conjugation plus parity. Uh, so that CP symmetry is there for such reactions. But in some cases, that will not be possible when you change that charge, which means that the particles interchanged with the antiparticles and vice versa, and the axis are flipped for this parity action. Then if that interaction is not going to happens in that order, then which means that the CP symmetry is not there. So it will not be conserved in that particular. And one such reaction is for that kaons when they decay, they do not obey this CP symmetry. They will not come. So it is not conserved in that particular that we discussed in the last class. Okay. So first we considered two different states for those kaons. This is just happened in 1964. After that, CP symmetry was there for all the interactions. It was allowed or it was valid for all the interactions, and CP symmetry or CP conservation was there. So both, if you have both charge conjugation and parity, then parity operation on any of that interactions, then almost all those interactions obeys this CP symmetry. But later, 1964, it was found that for some cases of those kaons decay, this CP symmetry violates. Okay. So we have we considered that first state of these kaons as K1, which is 1 by root 2. This is one of the state. So this is K0 we are considering now. So K0 minus its antiparticle, which is K0 bar, K0 bar. So this is the first state. And the second state, let's consider K2, which is equal to 1 by root 2. Same scenario. In this case, we have K0 here, and which is plus K0 bar. Right. So now when you apply that CP action, that is charge conjugation plus parity operation, getting those accesses. Then after that, CP action. Okay. So CP acting on that K1 state. That will give me 1 by root 2. No, CP acting on this, so that this K0 will become antiparticle because of charge conjugation. And then also this K0 will be having in the opposite direction, which will be opposite direction as compared to the previous state because of the parity operation. So I will get the first state I will get minus of K0 bar, then minus this K0 bar will become K0 because when you have the charge conjugation property, your antiparticle will become particle and particle will become antiparticle. So that will become K0. And also we have to apply that parity. So this direction will change. So this will become minus K0 plus here. Okay. And this is nothing but your K1. Because when you take this together, so K0 minus K0 particle. So this is nothing but your K1. But if you have the CP action here, the charge conjugation and parity acting on K2 state of this K1, that will give me 1 by root 2 times this one will be K0 here, so it is minus K0 bar, and this time this will become K0 with a minus I. This and this you can write it like minus 1 by root 2 of K0, K0 plus K0, and that will give you minus of your K2 state. Okay. So when you have this CP, that is charge conjugation and parity, which is acting on this particular state, you have eigenvalue here, which is plus 1. But in here you have that eigenvalue, which is minus 1. So that the CP acting on any state, charge conjugation with that parity, parity, that is CP, acting on any state, that will give you that eigenvalue and that state, and this eigenvalue we have here it is plus 1 and here it is minus 1. Okay. Now we consider the decay of K1, decay of K0 ions. That will be like K0 can go into 2 pions or K0 can become 3 pions. These two decays are possible. So when that will become 2 pions and the eigenvalue corresponds to these pions, when there is that CP action. So if you apply that charge conjugation and parity on these pions, then we'll get minus 1 for each pion. So thus eigenvalue correspond to that CP action on these pions. So for first pion we'll get minus 1, second pion will get minus 1. So the total CP eigenvalue will be minus 1 square. Here we'll be having total CP eigenvalue is 3 pion state, that will be minus 1 to the power 6. So for each pions we have CP eigenvalue which is minus 1. Okay, so that will give you that minus 1 to the power 2, minus 1 to the power 3. So this is nothing but positive 1. This is nothing but minus 1. Okay, then I can assume this state as my K1 state because it is having that plus 1 and this is nothing but my K2 because it is giving me negative eigenvalue. Here we can have that negative. So this is nothing but that K2. That K0 will be having this. Okay, and if you consider the kinetic energies of these ions, which are formed after this decay, so these pions will be having more kinetic. So these are having less kinetic. Okay, so which means that these pions, they have less lifetime, or we can say that they are short-lived. Okay, these are short-lived, but these pions, they are having less kinetic energy. They are having long life. Okay? Having long life or long life period. So as compared to this, okay, so which will be in the order of 10 raised to minus 7 seconds. So it is not like minutes or it will not be here for hours, but it is just 10 raised to minus 7 of order of seconds. But compared to this one, this decay process, when it becomes two pions, they live very shortly as compared to this. This will be there for much more longer, about 500 times more than this. Okay, so this will be having more lifetime. So I will call this state as KL with the kaons which are decaying into pions, and those pions will be having more lifetime. So these are long-lived pions, and these are Ks short-lived cases. Okay. Now, if you do some experiment to observe this decay process, and it is observed that if you have this K0 which is decaying, and you could pass this through some tube and observe that decay process, this pi plus pi, 2 pions and 3 pion states. And then it is observed that if these are short-lived particles, they cannot travel much. This, okay, and we cannot observe these particles. But it is observed that when this K0 decays, it will become 3 pions. Okay, it will become 3 pions in this particular decay process. But it also observed that this K0 sometimes it is decaying into 2 pions. So when this length is large and in such a way that we cannot observe these pions, these 2 pions in such system, uh, uh, according to these theories, we cannot expect these 2 pions in that system because they are short-lived. They cannot be there for long period, and they cannot enter to the other side of the tube because they are short-lived. So we cannot observe these 2 pions, this particular decay process for that long time. But here we can expect